Hello everybody! Welcome to our Embedded UI live series. Today we're talking about embedded task priorities and how you can take advantage of priority selection and task scheduling for the greatest effect with your embedded user interfaces. I'm Thomas Fletcher, Vice President of Crank Software and Head of our R&D department, one of the co-founders, and I'm going to be talking you through it today. I'm going to start out by saying we've had a few glitches in the past where people have waited until the end to ask questions, and then we go through our live session, then we sort of start gathering things up and winding down, and then all of a sudden the questions start coming in. If you have questions during the presentation, feel free to throw them in. I may not address them during the presentation, but certainly it's nice to have them so that I can scoop them all up and talk about them at the end. All right, let's get started. So why are we talking about embedded task priorities? Why are we sort of considering this in the context of embedded UIs? Well, what is important about most embedded UI configurations is the operating environments in which they're running. Most of them are running inside of an operating system or a real-time executive, and a lot of those configurations are, just like the name says, real-time. And what does that mean? That means that they're geared around the idea of providing deterministic response, right? Typically, these configurations are set up so that it's not just a matter of running multiple tasks, but the operating systems and the real-time executives are actually designed around being able to provide you with deterministic behavior, very reliable behavior. So if you have timing requirements, you have certain priorities that you need work to be done at, that you can ensure that that is being done in a regular sense. And so we can leverage that information and leverage that configuration when we're putting together our embedded UI, because now more and more these embedded UIs are running on the same systems that are doing the data gathering. So the same configuration that would apply to your data gathering in terms of task selection and priorities would also apply to your embedded UIs. As a little bit of a grounder, what I want to do is I want to give a bit of a baseline around scheduling policies and scheduling selection so that it puts the priority conversation into context. So for that, I'm going to pull up some slides here, a little bit of slideware. We're going to talk about 3 tasks, task A, task B, and task C, that are all coming in to be executed by the system. And what this is going to do is this is going to give us a little bit of a playground to work with when we talk about why I would make certain task selections. So these are 3 different tasks. They're all arriving at different times, a little bit offset from one another. They are all executing with a different amount of CPU resources. So task A requires 2 time slots, task B requires 1 time slot, and task C requires half a time slot. So if we were thinking about how we would execute these tasks in the context of their simple arrival, what we would find is we'd find that there'd be a configuration that would look a little bit like this, right? This is this natural sense of a job arrives, I'm going to execute the job, and then I'm going to look to the next job that's arrived, and then the next job after that until there's nothing for me to do and just keep working. This is FIFO scheduling, or first in, first out, right? The first task to arrive gets serviced, it gets serviced all the way to completion, and then the next task is serviced, and so on and so on. This is a very, very simple scheduling policy to implement, very straightforward, but it runs a risk of really not being very fair, right? Allowing one task to come in and simply dominate the CPU execution, which, it's not really, kind of the sense of what you want in a system where I might be running multiple activities at the same time. So there's an evolution of this, and there are lots of different scheduling policies. I'm only touching on a few of them here today. But the common ones are FIFO and, alternatively, round robin. A round robin scenario is one that kind of addresses the fairness of a FIFO scheduling, right? A first in, first out scheduling by saying we're going to service tasks as they arrive, but we're only going to service them for a certain amount of time before we stop and look to see if there's another task to service or execute. So in this case, what we see is our A task arrives, it starts being serviced, but it's serviced up until a maximum of T time, and then we switch to the next task, which in this case was B arriving, and then we execute that for its time, And then we switch to the next task, and the next task, C, is only half of a time slice. So we execute it, and then as soon as we're done, we go and pick it up again at A and sort of finish A off. Again, round robin, the idea here is that you're introducing a little bit of fairness, a little bit of sharing of the processor, and you're doing it in a way that's sort of deterministic in terms of, you know, that the worst case execution scenario is that you're going to be delayed by a certain time slice before you get a chance to execute. So that could be the number of tasks, sharing that priority band, and then, you know, coming all the way to you. And so that allows you to sort of calculate what your latency would be on a system. So this is a very popular scheduling policy. In fact, it's the default policy for a lot of embedded configurations and even operating systems that are kind of doing fair share, is that they have this sense of a time slice and that you'll execute, or you'll either own the CPU for that period or you'll execute till you block. So what does this have to do with priority selection? Well, if we want to start thinking about tasks as certain tasks being more important than other tasks, and what we like to do is when those tasks arrive, we really would like to execute them right away. This is where we end up with our priority selection. And priority selection is something that's a little bit different from operating system to operating system in terms of the actual nomenclature that they use, in terms of they're frequently numeric values in terms of the priorities, but sometimes 0 is a high priority, sometimes 0 is a low priority. So today we're going to talk about, you know, in an abstract concept, 2 priority bands, high priority and low priority. In reality, most operating systems, QNX, FreeRTOS, MQX, they're all going to have multiple different configurations, anywhere from 12 to 64 to 128 to unlimited priority bands. And that gives you a lot more freedom in terms of picking and choosing where tasks execute. So if we look now at our scenario, what do we see? So what we decided in this scenario is that we wanted B as an execution task to be prioritized above the A and C tasks in terms of importance. So that means that whenever B arrives, we would like it to preempt, right, take control of the CPU to perform its execution. And so we can have B scheduled at a high priority. When A arrives, it'll start executing, and it'll execute at its lower priority level, right? And this is the same as what we were seeing with our round robin scheduling. Once B arrives, there's an immediate preemption. We switch tasks to B because B is higher priority. We start executing B. We're running through. We're going to run B all the way to completion because it's the only high priority task that's running. When B finishes, we're going to switch back down and start looking at the lower priority tasks to execute. In this case, because A was preempted, A is still sitting at the front of the round robin queue, so we'll pick A up. Now this is, you know, something that could be changed from system to system. Some systems, when you get preempted, will put you to the back of the queue. Some systems will leave you at the front. In our case, we decided in this scenario, we're going to leave A at the front. A is going to execute, but A is only going to execute for its time slice before it gives control over to the CPU to C. And then C is going to run for its half time slice, and then A will pick up. So, you know, this sense of fairness combined with a sense of importance, right? And that's really what we're talking about when we talk about choosing scheduling policies, round robin, FIFO, you know, first in, first out, or other scheduling policies that are available, and then scheduling or choosing our task priorities in terms of what's the most important thing to run on your system and when do I want to have that task execute. So that's just sort of a quick, you know, kind of quick introduction and an overview. Now, why are we talking about that in the context of our embedded UIs? Let's put some numbers in place. So when we talk about task priorities and we talk about scheduling policies, inevitably we're talking about how I configure my system as a whole. All the tasks in the system, what's important to run, what's not important to run, and how long do these things need to run for. So when we're talking about user interfaces here, we're talking about wanting to achieve a relatively smooth drawing rate. And we've talked in the past of what that means. When we talk about smooth animations, when we talk about smooth movement across the screen, we're talking about 30 to 60 frames per second. You can go a little bit lower in certain scenarios. It really depends on the nature of the user interface, but this is a good, you know, sort of a good ballpark to be holding ourselves to.
So nominally what that translates to in terms of time is somewhere between 30 and 15 milliseconds when I'm doing my rendering, right? So this is 30 to 15 milliseconds in between my frames. That's the gap time that I'm allowed to have between frames if I would like to have a smooth visual experience. So these are important numbers now, because now what I can do is I can put this in the context of the rest of the system that's executing, right? The data collection tasks, the input tasks. I can understand if I need this to be the latency on tasks, that I need to be able to ensure that I come back to do my rendering in a timely fashion. Well, this is the number that I'm working with now. It's something that I'm looking at. There are some other numbers, because we're talking about user interfaces. A lot of times we're also talking about user input. So there's some other numbers that are worthwhile considering kind of in this context. And these are rules of thumb, right? Sort of best practices, and some of them are coming out of scientific studies where they've done analysis of people's interaction with user interfaces. And those numbers look like this. So 100 milliseconds is sort of our time frame for instantaneous, I'm going to get this wrong, instantaneous feedback. Right? For something to feel like it's happening immediately, that's sort of the latency between a triggering action or event in terms of user input and then some sort of response, right? So that 100 milliseconds is sitting well above, our render rate, right? So that's an interesting note. The other piece here, in terms of time, that's curious, is 250 milliseconds. 250 milliseconds is the average response time, right? The average response time for someone seeing something visually change and their ability to kind of react to it is 250 milliseconds. So when we're thinking about user input, we're probably thinking about thresholds that sit somewhere between this 100 milliseconds and 250 milliseconds in terms of your feedback to the user about what's going on. And then you want to put that in context of if what the feedback is going to be some continuously animated visuals, then we need to think about the rendering time that those visuals are going to have. So there's response time and feedback, and then there's the notion of how long is it going to take for me to actually provide that rendering. Now, just as kind of one other number that you'll often see is this notion of 1 second, right? 1 second for web interactive, right? For people to stay engaged with a web page, to stay engaged with a UI, this is sort of the rule of thumb, is that you don't ever want to be seen as kind of going off the rails or disappearing for more than a second. So this is your feedback loop, right? Being able to kind of make sure that people feel like they're still engaged with your UI. So these are numbers. What do they mean when we start talking about embedded UI configurations? So I'm going to ignore the system configuration, all the data gathering and all the other activities that go on in the system, because those all have their own time, sort of time priorities, time restraints that you have to meet as part of your embedded system. So I'm going to restrict the conversation here to really looking at two aspects of the embedded UI environment, and that's your input and your rendering, right? And these two elements are fairly important for interactive UIs because we want to make sure that we're putting that feedback, we're putting that presentation in the context of the rest of the system. You need to be able to gather data in a timely fashion, and then once you've gathered the data, being able to feed it back into the system. And we can take this conversation and take the input side of it and apply it to the data as well. So let's start out with a configuration where we might say naturally, as a high priority task and as a low priority task, what I would want to do is I want to consider my input, right? The feedback that I'm getting from the user, right? This might be on my touchscreen driver, the polling loop, the interrupt controller. When I get that input, say, for example, a press event, how do I respond and then draw with my UI, right? So the rendering block. So the idea here is that I want to maybe think as soon as I get a user input, I want to be able to turn that around and I want to be very responsive, right? So I'm going to put that as a high priority task, and I'm going to feed that data to my UI, and my UI, it's blocked most of the time. I'm going to put that as a low priority task. It's going to feed that data down. So that's an interesting, sort of proposition. If I did that, then what I might find is that for single press events, I get a nice story. I get a fairly responsive UI because as soon as my input is occurring, it's feeding data to my UI. The input stops. The UI displays, renders the content, processes the data. Great. What happens when I start seeing lots of these input events? Right? Maybe it's not just a press, but maybe it's a press and a series of motions. Think about what happens when you're interacting with a scrolling list, right? In this type of scenario, your inputs now are going to start bombarding your UI, and if you run your input mechanism at a higher priority than your UI, then this starts fragmenting, right? We talked about this being preempted. My rendering that was occurring here has to stop, and then maybe I get a little slice of rendering in here, and then maybe eventually I get a little slice of rendering in here, and maybe these were motion, right? Hard to see. I'll just put a big M here for motion events, right? Because we were dragging across, and eventually, what I get is I get an input event, and this is going to be my release, right? It's going to be a little messy drawing today. Well, the problem is that I'm still responding to my first rendering activity while all these input events are occurring, right? So something has to happen with those input events. They are either being queued and fed into the UI in terms of some sort of an input mechanism, and they're being all queued up. What does that mean? Well, that means that because my rendering is occurring at a lower priority, I'm going to start processing all those motion events afterwards and then the release events. So then what happens is I'm going to see this sort of lagging notion as I click on something and maybe drag it around. It's going to lag my finger. It's going to lag my input. So the way that gets corrected typically is that there's some sort of compression that happens in here, where those motion events will be compressed together. So that instead of here we have two motion events and then a release, those motion events might get compressed together into a single motion event. So you'll drop this event. You only work with the latest one. Or perhaps you'll maybe drop all of them all the way to the release, in which case you're not lagging anymore, but what you're getting is you're getting a feeling of being very jumpy, right? In a scrolling scenario where I'm going to draw, chunk, draw, chunk, draw. And the problem here is that we don't have control over this. We don't have control over what the user input is going to be doing. This might be serviced by interrupts. So we could put logic in here to say, well, I want to preempt, but I don't want to inject events until the rendering is finished. That's a lot of logic for your input to handle. The compression in a framework like Storyboard is typically handled transparently, so you can feed as much input in, and we'll compress that input in a smart fashion to give you the best experience. But you're still paying this cost of constant preemption on your rendering path. And this cost, right, we show it as kind of an immediate transition, but it takes time, right? It takes time for one task to be torn down, for another task to be started up. So there is, in fact, a delta cost here that adds up for every time you are doing a task switch and preempting. And ultimately, on systems where you may have a low power CPU and every cycle is critical, these deltas can very rapidly add up, right? So that's one configuration where our high priority task is really our input task and our low priority task is kind of the UI and the rendering. So let's flip that around. Let's think about a scenario where we reverse those two. So
most UI frameworks, storyboard included, are going to be event-driven, right? They're going to be sort of sitting in some sort of a passive state, unless it's kind of more of a movie, HTML, browsers, right? There's something that's constantly always going. But in our embedded environment, really we want to be totally event-driven. So our UI, which now is a rendering task, we'll say is sitting up here and it's just passively waiting for input. Now what we can do is, as we receive input, if our input was slightly low priority, and I mean low priority, high priority relative to one another here, right? We can still place these in the system to allow us to have a certain level of responsiveness. When that input occurs, this was our press, we're going to start rendering again, right? We'll start the data processing activity. We're going to start the rendering activity. When that occurs, now what we have is the UI has control over seeing the rendering through to completion. And this is important because, remember, we need to make sure that if we want to have a smooth data flow, that we're sitting between this 30 and 15 millisecond interframe timing, right? So when I do my rendering here, maybe I've got other input events that are occurring, and these may be driven by interrupts, so they may actually be interrupt-driven components, but we're not going to be actually servicing the data. And so here your hardware may drop the events, right? You may simply see a replacement of the events. That's that natural compression that's happening up here. But when we're finished rendering, we're going to be able to process that again. Now, remember, what we want is, from a response time, in order for an instantaneous feedback feel, we want this time here to sit in the 100 millisecond range. But our rendering time, right, if this input was triggering another rendering block, this rendering time here, we want it to be 30 to 15 milliseconds. Because the UI being more event-driven, it's going to be passive until it actually has an activity to perform. So if I'm doing an animation, then I can actually interweave these inputs along with the animation processing and kind of give you a smooth rendering experience. But I'm also not segmenting up and constantly preempting my rendering, which is actually buying me all these little bits of time. So it's an interesting consideration, right? It's sort of this trade-off of input and the responsiveness of the input to the scenario of I want to have the smooth drawing and the smooth feedback. And this 100 milliseconds here, this is all at the control level in terms of your data flow, right? If I have data flow that's coming in from outside sources, I want to be able to kind of consider the effect on the UI in the same way, right? And so I may want to prioritize the acquisition of that data, but because the engine, in Storyboard's case, knows about input events as a special class of events that can be compressed, when you're doing your interaction with the UI in terms of the feedback, you may be looking at saying, well, I'd like to introduce my own compression because I understand the data that's coming in from the outside world and I understand what I can compress and what I can't compress. So it's this trade-off, right, of being able to kind of balance back and forth. Now, one of the scenarios we haven't talked about is we talked about using the task priorities in terms of segmenting. What would happen if we had a round-robin system, right? If we put this into a round-robin system, and maybe I can just grab some space over here, we would have something that would perhaps look a little bit like my input task gathers, my render task is executing, I'm capped here at some time frame, right? So if I have a time slice that makes sense in the context of, sort of how frequently I would like to time slice between my tasks, then I have the possibility that I could end up with not necessarily an optimal system, but something where I'm getting the best of both worlds and I'm consolidating it all into one process band. Again, there's no black and white answer on these topics in terms of the best thing to do. But what's important is to understand how embedded task priorities and how embedded task scheduling all come together to sort of feed the system and give you a particular experience. And the numbers, the values that you're going to be looking at in terms of your UI, the nature of your UI, maybe your user interface is purely event driven in terms of its presentation. Maybe there isn't a lot of rich animation, a lot of rich movement that's going on. And so in that case, you don't need to be as concerned about this 30 to 15 millisecond time frame, because you're not going to be doing sort of these smooth animations. You really are going to be reacting to input and updating the display. Lots of things to consider. I'm going to take a look and see. I see there's some questions coming in here. When performing multi-scheduling, is there any potential of each thread accessing memory that belongs to another thread or the RTOS itself? Absolutely. So that's a consideration we've kind of ignored here. When we talk about these two tasks, right, our input task and our rendering task, we're sort of assuming that they kind of live in independent worlds. But this communication back and forth has to occur in some sort of shared space. Typically, an operating system will provide some sort of a messaging service between tasks that can be synchronized so that you don't end up with any data corruption between the two elements. This is something that typically takes the form of something like a message queue, right, or event queues. Inside Storyboard, we also have the same mechanism, and we have protection between tasks that are executing. So you need some synchronization primitives there anytime you have shared data. But the operating systems will typically provide that for us. And when we use Storyboard I/O, if you're using Storyboard I/O or the Storyboard Event API to inject data, then that's all covered for you. You don't have to worry about that. There's no shared data that goes back and forth between these two that's not protected by some sort of synchronization primitive. What should be the RTOS tick rate on an embedded UI? Any recommendations? That is a fantastic question. And that's something that we often see as a consideration for sort of performance improvements. A lot of embedded systems that come with real-time executives, right, these free RTOS type configurations, will start out with a tick rate of 10 milliseconds. What's the challenge with a 10 millisecond tick rate? Well, the challenge there is that if you're looking at trying to render every 15 milliseconds, but your system is really only doing bookkeeping every 10 milliseconds, you're pretty far away from being able to accurately drive in on that 15 millisecond inter-event timing, right? So the task, there's two considerations. One is the granularity of your clock, the granularity of the system tick, and then in the case of round robin, there's the granularity of what the time slice piece should be, right? This question mark here. What is this time slice? So the time slice tends to be highly configurable, right? This is something where you are going to look at the nature of the tasks that are executing on the system, not just the UI task, but all of your system tasks, and decide what's appropriate here, right? You need to strike a balance between interrupting tasks too frequently and allowing them to have enough time to actually do the work that they need to do. Because as I mentioned, task interruption, task rescheduling, it accumulates silent time, right? Time that's not really accounted for in the system. So usually when we look at systems, we like to have a 1 millisecond tick rate, because 1 millisecond gives us 2 milliseconds of granularity in terms of making time assessments, right? This is your frequency split rate, and you can move that up. You could move it to a 5 millisecond if you're finding that's too taxing on your system. At 5 milliseconds, you're looking at a 10 millisecond granularity, right? Because you may have come in to make an assessment a little bit one side or a little bit the other side, so you can only be guaranteed that you're truly measuring at a 10 millisecond resolution with a 5 millisecond tick rate. This kind of gets into kind of measurement theory and your sort of some complicated priority and task scheduling kind of conversations, but we can tune these things on our embedded systems, and we can sort of look at the conversation we want to have here and put that into context for those selections. So that's a bit of a waffling answer, I know, my answer is usually, if you want smooth animations, you've got to be in the area of, sort of 1 to 5 in terms of your tick rates, because we need to be able to make assessments, and those assessments then are going to be applied to all the animation work that you're doing, and then put into context with the rendering activity. Is there a way to reduce the deltas that occur during rendering? Any suggestions? So these deltas, I think, is what Steve is asking here. Steve's asking, can we reduce these deltas? Well, the first way to reduce those deltas is avoid the preemption, right? As you look at your task, as you look at your system, you want to take a look and see how frequently things are being interrupted. Now, there are great tools for this available with most real-time executive and real-time operating systems. On Unix, for example, you've got your system profiler. On Linux, you've got the tracing toolkits. On FreeRTOS, these embedded systems, you've got tools like Percepio, which are going to give you the insight into the system to be able to measure how frequently you're interrupting, right? So then the first thing is you reduce the deltas by reducing the interruption. Get rid of the problem altogether by not having the problem. If you want to reduce the costs here, that's an interesting question, because a lot of that is buried at the operating system level, right? And that is really going to be a processor-specific thing, and these costs tend to be pretty fixed. It's not a matter of I have more tasks or less tasks. Those tend to be fixed. But what you can do is you can look at this cost here. What's the cost inside my rendering block, right? How much work am I doing inside the UI rendering, we'll call this task, that isn't about rendering? And this is where you want to be able to mitigate the amount of data processing, for example, that you're doing. If I'm responding here on a press, I'm interacting with my UI, I'm pressing, and my UI is doing some work to respond to that feedback, maybe it's doing 2 parts of work. Maybe it's a button. The button is visually changing, so that's going to be my redraw activity. But the button may also be performing, in storyboard terminology, an action. And then that action is going to be executing in this context. What do we want to do? We'd like to move that off to some other context, some other task, right, as quickly as possible. So get it out of the UI, get it out of the rendering path, move it into a system path, and that can be configured in the context of the rest of the system here, right? Move that data, move that kind of announcement, whatever is being generated by the button in terms of some sort of imperative command, push that down into another task, right? Some lower priority task. And then you want to move all of your data out that way, right? And that's good practice, right? Because it keeps your UI clean, the data processing separate. So I think that looks like we're kind of hitting the end of the questions for today. Bit of a long session today. Scheduling, task priorities, real-time operating systems, it's a passion of mine. I like to talk about it. But it's also really, really important because it's not just a cut and dry solution of make it high, make it low. You really have to understand what high and low means and what it means in the context of your system. And my colleague Gary did a great webinar using the Percepio tools where they did an analysis of a running system, running with storyboard, looking at how scrolling worked, capturing a trace, and then making adjustments to these input, not the priorities in this case, but the input polling rates, right? They were looking at how frequently things were being interrupted here to give a smoother experience. And in their case, they actually made some adjustments where they moved the time down to give a better effect because they could see what the rendering cost was, and they could see the input, and they knew that they could move things appropriately and still end up with the right responsiveness that they were looking for. My colleague Sarah is also going to be talking about the context of scrolling and embedded UIs in an advanced user tutorial for Crank software later this month. I'd encourage you to take a look at both of those web activities. One's a webinar, one's going to be a sort of a presentation. My next Embedded UI Live session in 2 weeks, we're going to be doing one of our last ones before we kind of put things on hold for the summer. We're going to be talking about glue logic in your embedded UI. We're going to be talking about how you can effectively connect the UI to your embedded system. Now that we've got this context of prioritization and knowing that we want to kind of move data out, how do we do that? What are some of the techniques? And more specifically, we're going to be focused on callback approaches. So thanks a lot for tuning in, and we'll talk to you next week. Thank you.